Welcome back, everyone. This is Ben Mounts, and this is the follow-up video to a video that I previously shared where I had created a protractor and a ruler that we can use in Keynote along with Apple Maps images to measure vectors along the ground. A vector being something that has a length, but also a specific direction as well. And so that the ruler can be used to measure length, and then of course the protractor can be used to measure direction. Let's move that around there like that. All right. And what we found was that we added up all these different vectors. We had gone from home plate right here to someplace down here, and then up there, and then down here to this third point. We measured all those vectors, and then the result of all those, so I can make this menu go away. I'm gonna make it go away, and I don't know why it's not. There we go. The result of all those is this we have at the bottom right here, 66 meters at 57 degrees south of west. Now we did that all by using the ruler and the protractor. The only thing is that adding vectors together like that with a ruler and a protractor isn't always the most convenient. It's certainly accurate, and we could measure the resultant that way, going from the original starting point to the final destination, measuring the angle right here and measuring the length that is a magnitude. But the purpose of this video is to show how to do it mathematically as well. All right, and so what we're going to do over here on the right is take our three original vectors, which I have written here in yellow, and I kind of transfer them over onto this grid right here. And we're going to add them together mathematically and see how close we get to that original 66 meter length at 57 degrees south of west direction that we arrived at in the first part. All right, so I'm going to go ahead and kind of go full screen right here, and we have these three vectors, but the problem is you can't just simply add them end to end because they're going all different directions, and they all have a certain length, but those lengths aren't in the same directions, and so you can't just add 53 plus 52 plus 32 and get your vector distance. Oops, I lost a 3 right here. You can't get your vector distance, but rather you need to do it mathematically. And what we had was, we had our starting point right here, and our first vector, vector 1, was something like that. We'll say that's 53 meters at 73 degrees south of east. All right, 53 is the length, 73 is the angle. Our other one, we had 52 meters at 32 degrees north of west, and so that was kind of up here, and maybe something like that. 52 meters, and that's 32 degrees north of west. Let's fix that a little bit, that 32 degrees north of west right there. And our last vector was 32 meters length at 85 degrees south of west. So very nearly vertical, but in the southwest quadrant. And so kind of going southwest from that direction right there. Maybe something on the order of, like say that. I want to say that magnitude is 32 meters, and this angle right there is 85 degrees south of west. And remember, each vector is kind of like its own starting point. Let's just put a red dot at the origin for that vector here, and then we've got another origin for that vector there, another origin for this last vector right here. And so when we add them together, as we say, tip to tail. I'm going to put a green circle at the starting point, and I'm going to put a red circle at the end point right here. And this value, that magnitude and that direction, are what we had measured in the last segment. That is, let's go back to Keynote here real quick. That magnitude and then that direction right there should be what I just kind of outline for you. The thing about vectors is that you can add them together tip to tail, but it doesn't matter what order you add them in. Let's say I'm going to take this. Actually, I'm going to see if I can get the little red thing there. All right, we got this vector here and this vector right here. I'm sorry, I'm going to leave that red dot behind, unfortunately. And we're going to add them in a different order than we had them previously. I'll put that red dot right back there. Okay. Let's say we did this vector first, and then we did this vector second. I can put that right on the tip of the first one, to the tail of the one. And this vector third, what you're going to see is if I've done this right, it's going to get us to exactly the same spot. Or if I move these around and add them in a different order, this guy first. So that'll go way up there. That's going to be kind of messy. This guy first, like we had before, and then this guy, and then this here. It's still going to get us into the same spot. And what we're effectively doing is we're adding up all the, to get this resultant vector from here to here, we're going to be adding up all the x's and all the y's of each of these vectors. And spread them back out again. All right. Each of these vectors has some sort of component in the x direction and some sort of component in the y direction, positive or negative. All right, do this over here as well. This one's going to be really close to the vector itself. There's the y component, and the x component is going to be this short little guy. And the same here as well. There's your x component, and here is going to be your y. Oops, let's fix that. Your y component. Like that. And even though the vectors themselves, this, that, and that are not, you can't add them together because they're not all in the same direction. The x and y components, you can all add together. Because if I were to take, put that there, and take and put this vector right here to kind of get us to the very end point, we could add all of the components together and get our resultant. That is, put all the components together. So let's see here. So put the tail of the one on the tip of the previous one. So these kind of like negate each other a little bit. And then this one right here, like that. And then we have this guy, put the tail of that one on the tip of the first one. And this one over here, I'm going to come back up like that. So it goes down and then up to right there. This guy goes over that way and then back like so. And so that means that the resultant vector should have the total y component of that and the total x component of that. But like I said, I've been doing this all kind of geometrically right here. And it can almost be a little bit confusing if it's not confusing already. Let's mathematically find out what the x and y components of each of these vectors are. In fact, let's put them all back. Like say, like that. All right. And instead of drawing them all out, let's do it. We're going to add vectors mathematically. And I'm going to do this by setting up a table. All right. My table is going to look like this. V, that column is going to be for vector, the vector name. Vector 1, vector 2, vector 3. Mag, that's short for magnitude. That is the length of it. Could be in any direction. Third column is going to be theta for direction. Fourth column is going to be x. And the fifth column is going to be y. That is going to be the x component and the y component of each vector. So let's kind of separate these out a little bit, like so. And we're going to be adding together vector 1 and vector 2 and vector 3, and hopefully getting whatever vector 4 is going to be. But here's our plan of action. We're going to take the magnitude and direction of each of these vectors and figure out what their x and y components are, add all their x components together, add all their y components together, so we've got a resultant x and a resultant y, and then work backwards to figure out what the magnitude of vector 4 and what the direction of vector 4 are going to be. All right, and hopefully it's going to be close to what we measured with the ruler and the protractor. Well, vector 1's magnitude is 53 meters. The direction is 73 degrees south of east. South of east. Now I put like a little arrow in there like that. That's southeast or south of east. That means it's got a positive x direction, but it's got a negative y direction. So positive, I'm not going to do anything with, but the y direction, I'm going to put a negative sign right there just so I know. Just so I remember that that's going to be in the negative y direction. What about vector 2? Vector 2 has got a magnitude of 52 meters. The angle is 32 degrees. 32 degrees what? What quadrant? North of west, which is in that direction. So that's going to be a positive y, but a negative x. I'm going to put a negative in my x right here. And the third one, vector 3, 32 is the magnitude, 85 degrees is the direction, and south of west is like that. We're going to have a negative x and a negative y. So I'm going to put a minus sign there and there as well. So how do we actually get the x and y components? Well, the magnitude is effectively the hypotenuse, and this is the theta is the angle. And if we're talking about angles measured from the horizontal, and that means then the x component would be the adjacent side, and the y component would be the opposite side. In other words, to get the x component, we would take the magnitude times the cosine of the angle. That's like saying your adjacent side is the hypotenuse times the cosine, which is true. And the y component would be the magnitude of the hypotenuse times the sine of the angle, because it's opposite. It's opposite of the angle. So let's get our x component for vector 1. Magnitude times cosine theta, so it's going to be 53 cosine 73. It's 15.49, 15.5 meters. I lost that. There we go. That point right there. How about the y component? 53 sine 73 is going to be 50.68. I'm going to say 50.7. I'm rounding a little bit, so there's going to be some error, but that's okay. Second vector, x component, magnitude cosine of theta. It's going to be negative, right, because it's in the negative x direction. Magnitude cosine theta, so it's 52 cosine 32. All right, so 42.59, we'll say 42.6, and the y component, which is going to be magnitude times the sine of theta, so 52 sine of 32, 27.55, let's say 27.6 meters in the positive y direction. And our last one, we've got our magnitude is 32 and our angle is 85, and both the x and the y are going to be negative, right? Because you've got negative x and negative y. So 32 cosine 85 is 2.78. We'll just say 2.8. 2.8 meters in the negative x direction, and the y component is going to be 32 sine 85. 31.87. We'll say 31.9. That's going to be in the negative y direction as well. So what we've done is we've found the distances that each of these vectors go. I should really say the displacements of the vectors go in the x direction and in the y direction And since these are all in the same respective directions, we can actually add them up. So let's go ahead and do that for x and for y. X is going to be 15.5 minus 42.6 minus 2.8. And that gives me negative, sorry about that, 29.9 meters. What about in the y direction? We've got negative 50.7 plus 27.6 minus 31.9 negative 55. So we're saying that the x component of our resultant vector is going to be 29.9 in the negative x direction, and it's going to be, this is definitely not to scale, but it's going to be 55 in the negative y direction. So that means we should be able to solve for our actual hypotenuse, or that is the magnitude. Magnitude equals what? And the angle as well for vector 4. And that's what we're going to do now with these two sides. We have basically the two legs of a right triangle. And for the magnitude, we want to solve basically for the hypotenuse. And so we're going to use the Pythagorean theorem. We know that x squared plus y squared equals hypotenuse squared. So the magnitude squared equals x squared plus y squared. If we're going to solve for the magnitude, let's just square root both sides. So that'll go away, and we're just going to put a square root over there like that. All right, and so what is our x and y? X is going to be 29.9 squared. And you might say, where did the minus sign go? Well, I left it out because if you square a negative anyway, it's going to go away. Plus the y squared, it's going to be 55 squared. 29.9 squared plus 55 squared, square root of that, 62.6. 62.6 meters. That's going to be our length, or our distance, you might say, of our resultant vector. I'll put these kind of all in a straight line like that. All right. Lastly, so our magnitude is going to be, put back here, 62.6, and I'll put that in here as well, 2.6 meters. At what angle, what direction is that going to be? Well, if we go back to our trig functions, we know that if we have this angle right here, we have the adjacent side and we have the opposite side right here. And if you recall in trig that the tangent of an angle equals opposite over adjacent. That is, the ratio of the opposite to the adjacent side is going to give you the tangent of that angle. Well, if you want the angle itself, how do we undo that tangent? We take the inverse tangent of that fraction, or that ratio, opposite over adjacent. That is to say, the inverse tangent, or the arctangent, many people would say, of opposite, that is 55 over 29.9. And again, since we have negatives over negatives, then you're not worried about, well, I just took the negatives away, so you got a negative over negative, so that's why I didn't put the negatives in there. What do we get for that angle? Inverse tangent, arctangent of 55 divided by 29.9, I get 61.4 degrees. Let's go back here, 61.4. Now, what quadrant is it in? Well, we've got a negative x, and we've got a negative y, right? Negative x, negative y. That must be south of west, right? Because this is west and this is south. So our angle measured from the horizontal is south of west. SOW. Let's keep that all the same color right there. All right. South of west and south of west. And that is going to be our final answer. So our resultant vector, vector 4, should be 62.6 meters at 61.4 degrees south of west. Now, keep in mind, we did some rounding, and when we measured our initial vectors, we're using the ruler and the protractor, but there's a little bit of error associated with that as well. Let's see how well this 62.6 meters at 61.4 degrees south of west matches up with our original answer that we measured kind of by hand. We got 66 meters at 57 degrees south of west. So we're off by a few meters, a few units in the, we'll find my eraser right here. Sorry. Off by a few units here, and we're off by a few units here. But for the most part, we're in the right ballpark. It's about 60 meters at about 60 degrees south of west from this home plate to the sprinkler that was faulty. All right, so this right here has been my, we'll call it the component vector addition method. And that's how we can take vectors, break them up into X and Y components, and then use some trig to work backwards to figure out what's the magnitude and what's the direction of the resultant vector of all these that we're adding together. So thank you so much for following along. If in fact you're still with me, I do appreciate it. I realize it may have been dry at times, but there are manifold applications for this in the real world, as well as in math and science classes, and cartography, I'm sure, geography as well. So thank you so much for your time, and I'll see you on the next one. Take care.